Chapter 4, Chemical Quantities and Aqueous Reactions. This first little bit is kind of interesting. I'm not really going to test you on it. It just kind of serves as an introduction to the chapter. I think we're all aware of the idea of global warming and greenhouse gases. The greenhouse gases trap the warmth from the sun, much like the glass roof on a greenhouse traps the heat. And we need those greenhouse gases, or our planet would be really, really cold and we would die. Or we actually wouldn't be here at all. So scientists have been measuring temperature changes and measuring carbon dioxide in the atmosphere. And if you look at these two graphs, it kind of looks like there's a correlation here that over the years carbon dioxide levels have risen and global temperatures have risen. Now, you can present data in many ways and kind of make it look how you want to. If you look at this, what's the variation here? It's from minus 0.4 to plus 0.6. That's a variation of 1 degree over 20 years. 220 years, right? CO2 levels have risen 38%. There's this average rise of 0.7 degrees in the atmospheric temperature since 1860. So, depending on your point of view, you may think that's very significant or completely not significant. I'll leave that up to you. But the question is, are the two trends causal? Is one of them causing the other? Or is it just coincidence? Because if the CO2 levels increasing are not causing the temperature, then what point is there in trying to reduce carbon dioxide levels? One source of carbon dioxide in the atmosphere is combustion reactions. When we burn fossil fuels such as octane, combines with oxygen, forms carbon dioxide and water. So that's one source of carbon dioxide. Another source of CO2 is volcanic action. So there are natural sources of CO2, and then there are man-made sources of CO2. How do we know whether global warming is natural or because of our use of fossil fuels? I'll just run this one into the next one. Well, if we look at this balanced chemical equation for combustion, we get a relationship between the number of particles of C8H18, which is octane, and the number of carbon dioxide molecules that are created. We see that we get 16 CO2 molecules created for every 2 of these molecules that are burned, or 16 moles for every 2 moles of this. So in this chemical reaction, the amounts of each substance used, the reactants, and the amounts of the substances made, which are the products, are all related to each other. So we have the law of conservation of mass that we've talked about. You can't create or destroy mass. It can change form, you can rearrange the atoms, but you're going to have the same mass that you ended up with. And so we're going to have, because of conservation of mass, we have to have the same number of atoms of each element on each side of that reaction arrow. And when we look at the number of the numerical relationship between the chemical quantities, that's called stoichiometry. So you'll see that word off and on. Reaction stoichiometry means we're talking about the amounts of reactants and products and how they relate to each other. In a chemical reaction, we have the formulas for the compounds, and we have their state symbols, which tell us what state they're in. And then we have these coefficients before. And these tell us relative amounts in moles of each substance. We can interpret them in terms of numbers of particles, like this, 2 molecules of this, blah, blah, blah. Oops. Or we can talk about 2 moles of octane reacting with 25 moles of oxygen. And that's generally more useful because it's hard to do reactions with just one or two molecules. But we can pull conversion factors or relationships out of this. For every 2 moles of octane, we're going to use 25 moles of oxygen. So this is a relationship that gives rise to a conversion factor. And for every 25 moles of oxygen, we get 16 moles of CO2, and we get 18 moles of water. So now we're going to think about pizza, and I hope you guys got something to eat, because it is supper time. So I hope I don't make you hungry. Let's pretend we're making pizza. It takes a crust, 1 crust, 5 ounces of tomato sauce, 2 cups of cheese to make 1 pizza. Just a simple cheese pizza. A chemical equation is a lot like a recipe. It says you put these things in, and this is what comes out. And it gives amounts, right? When you have a recipe for pancakes or something, it matters how many eggs you put in there. And so if we're looking at this equation or recipe for pizza, the number of pizzas that you can make depends on how much stuff you have. And we can express this mathematically. I know you're thinking, why would we want to do that to pizza? But 1 crust to 5 ounces of sauce to 2 cups of cheese to 1 pizza. These are ratios. And we can use those ratios to calculate how many pizzas could we make if we had 10 cups of cheese and plenty of everything else. Well, 10 cups of cheese, we get 1 pizza for every 2 cups of cheese. And so we could make 5 pizzas. We can get conversion factors like this from the chemical equation. Here's the 2 cups of cheese, and that will give us 1 pizza. And so those 2 things from the equation become our conversion factors. In a chemical equation, it has to be balanced. The coefficients also act as conversion factors between the amounts of moles of reactant and product. And we can relate reactants to each other, or reactants to products, or products to each other, any combination. Let's look at this reaction again, this burning of octane. If we burn 22 moles of octane, how many moles of CO2 are going to form? We know that if we burn 2 moles, we're going to get 16 moles of CO2. So that's our relationship. It's a conversion factor between moles of octane and moles of CO2. So we start with the moles of C8H18, octane, and we're going to put the units in so they work out. We want to divide by moles of octane so those cancel out. We want to multiply by moles of CO2. The 16 comes from the balanced chemical equation. The 2 comes from the balanced chemical equation. Actually, I'm just pointing at these. I could be writing all over this thing. So the 2 is right there, and the 16 comes from there. So we get 22 times 16 divided by 2, 176 moles of carbon dioxide. Any questions? So that's nice, moles to moles, but we don't measure things in moles because moles are counting units. We measure things in grams. And so we need to use, here's in the middle, moles of A to moles of B. That's what we just looked at. But we're interested in what mass of A will produce some mass of B. And so this is our overall plan for stoichiometry, our map. Grams to moles to moles to grams. And you just kind of chant that until you wake up in the middle of the night, saying grams to moles to moles to grams. And it's like the key to doing these stoichiometry problems. You have a mass of A, and how do we convert from mass to moles? Remember? Molar mass, right? We calculate the molar mass. It relates the number of grams to the number of moles. Moles of A to moles of B, we use the coefficients from the balanced chemical equation. And then moles back to grams, we use the molar mass for whatever B is. So let's do an example. Lots of words in this problem. According to the U.S. Department of Energy, the world burned 3.1 times 10 to the 10th barrels of petroleum in 2010. the equivalent of approximately 3.5 times 10 to the 15th grams of gasoline. Calculate the mass of carbon dioxide emitted into the atmosphere using the combustion of octane as the representative equation. These things are going to be approximate, aren't they? Because nobody went around and measured exactly how much petroleum was converted into gasoline and burned. So these are all estimations. And gasoline is not just octane, but there is octane and similar things in gasoline, and so it represents gasoline, which is a mixture. And then we're supposed to compare this to the amount of CO2 that volcanoes produce. Not sure exactly how they estimate that, but I'm sure they have their ways. So lots of stuff going on in this question, but this is what we need. Here's our mass, and it's gasoline, but we're told to look at the combustion of octane. So we're going to take that to be 3.5 times 10 to the 15 grams of octane. From that equation on the previous slide, we know that it's C8H18. And we're supposed to calculate the mass of CO2. So we need our balanced chemical equation, so I'm going to write it up here real quick. It was 2C8H18 plus 25O2 gave 16 CO2 and 18 H2O. And our big idea of our path is grams to moles to moles to grams. So we have a given mass of octane. We're going to convert that to moles of octane. Then we're going to convert that to moles of CO2 and then to grams of CO2. Do you remember doing stuff like this in your previous chemistry class? Good. I don't want to bore you to tears, but I don't want to blow you away and have you not understand it either. So these calculations are generally going to have three terms. So we're going grams to moles. It's really important to write your units. Moles of the first thing to moles of the second thing to grams of the second thing. Grams to moles to moles to grams, grams to moles to moles to grams. And it's just dimensional analysis. We're going to stick our units in so they work out. Those guys cancel. Moles of octane cancels. Moles of CO2 cancels. Units first, then put in the numbers. This middle guy is easy. He comes from the equation, balanced chemical equation. So we find CO2 and we look at the number in front of it, 16. That's the number that goes in front of moles of CO2 down here. And here's C8H18. There's a 2 in front of it, so the 2 goes down here. Then we need the molar mass of octane for the first term and the molar mass of CO2 for the second term. So we'll just make a little note down here. It's always a good idea to write out your molar mass calculations, just so you can look back if you made a mistake and see what went wrong. So 8 times the mass of carbon and 18 times the mass of hydrogen.
We have this equation memorized,
The grams to moles to grams?
well, not that, but the top part, like the C8H18.
No. No, you don't need to memorize the chemical equations. No. They will, at the very least, They would give you the names of the reactants. And then you could you can predict the products and balance the equation. 8 times 12.01 plus 18 times 1.008 equals 114.224 grams of C8H18 is equal to 1 mole of C8H18. So in the molar masses, the number 1 always goes with the mole, and the other number always goes with the grams. And then we need the molar mass of carbon dioxide, 12.01 grams plus 2 times 16 grams is 44.01 grams. CO2 equals 1 mole of CO2. So 44.01 goes in here. Any questions? These sorts of calculations we do a lot of, and we do variations of them. And so if it's not clear, now's the time to ask questions. 3.5 EE15 divided by 114.22 times 16 divided by 2 times 44.01 equals how many significant figures should this have? 2. So 1.1 times 10 to the 16th grams of carbon dioxide. So that's the answer to the first question, calculate the mass of CO2. It's asking us to compare that to what volcanoes produce. But it gives us the volcanoes in kilograms. Let's convert the kilograms to grams. Kilograms on the bottom. What does kilo mean? 10 to the 3. So 10 to the 3 up here. So that's 2 times 10 to the 14th kilograms. I'm sorry, grams. So how do they compare? Well, what if we take the big one and divide it by the small one? See what we get. Divide by 2 EE14. It's 54. So 54 times as much carbon dioxide from fossil fuels as from volcanoes. So is it reasonable to think that combustion of fossil fuels could be contributing to the rising carbon dioxide levels? Yeah. It's bigger than what volcanoes are putting out. Any questions?